I think this is the first time that you're joining, right? Is it?
This is the second time, actually.
Oh, the second.
I couldn't join the last one, but I saw the YouTube video where everyone introduced themselves. So I know, or I saw the introductions of everyone, so I kind of know everyone, but maybe no one else knows me. I'm a student. I'm a PhD student at the University of Stuttgart. Uwe Eret is one of my co-advisors, and also Professor Gupta is part of the people who are advising me. So, yeah.
Awesome, welcome.
Thank you very much.
And yeah, also, I think it's the first time for Antoine. So
Yeah.
if you want to introduce yourself.
Yes, so my name is Antoine. I have a math bachelor degree and a data science master's degree that I got in 2019. And then I was working for 3 years in Extralab, which is a small startup company, and we build in situ water quality analysis laboratories we're going to put on the field. And the U of I is our client, and that's how I got into the U of I as well as student now, and I'm a PhD student with Professor Pravin Kumar. I'm going to be working in AI, linked with climate change and extreme events in a general manner, civil engineering.
Awesome, welcome.
Thank you.
Steven, I think it's a good time to start.
Yeah.
So, yeah, a quick introduction of our topic today. So, Steven is going to be leading the discussion today on this interesting paper. The title is Improving AI System Awareness on Geosciences Knowledge, Symbiotic Integration of Physical Approaches and Deep Learning by Jiang et al. In 2020. So, yeah, Steven, the floor is all yours.
Thanks. Yeah, so this paper is basically trying to solve the problem of combining the strengths of physically based modeling and AI for hydrological prediction by using some hybridization approach. So basically they say that they can represent the geosystem dynamics via the combination of a recurrent neural network with deep learning, but then also having a physics-aware part in it, which is basically I would say, a conceptual hydrological model. Yeah. And then it also can use an external module for the parameterization, which helps learning across basins. So but we'll get to that. Yeah, so basically in the deep learning versus physics-based debate, we have usually seen that deep learning is very efficient in learning from data, like a baby, but still babies are pretty incapable in general, and that's because they don't have a lot of experience. So physics-based is kind of building on all the experience that we already learned from data, like a typical professor does. So in a way, we're looking for a professor with baby capabilities. And that's why we need this hybridization. So this is the first hit output of the DALL-E generative AI, where a professor or a baby dressed as a professor presenting about hydrology, photorealistic. It's not very optimal yet. So basically, the authors distinguish three approaches for emerging AI and physics-based models. One is the surrogate modeling. So you're basically taking a physically based model, you let it simulate some outputs based on some inputs, and then you let the AI model learn the behavior of the physically based model by minimizing the loss function between the outputs of the physically based model and the AI surrogate. So this is, for example, useful if computational cost is an issue for the physics-based model, right? There's often these very complicated numerical models that take a long time to run, and maybe the actual behavior of the system can be simplified. So that's a good approach for that. Then in case B, we're basically using a physically based model to generate outputs, but then we use the observed values and the errors between the outputs of the physically based model and the observed values to train an AI model to basically do the error correction. So that's kind of putting them in series, if you will. And then the last approach that the authors kind of promote is a real hybrid approach where you train a model based on data, but there's physical knowledge encoded in the system equations. So the way they do that in this paper is they incorporate this PRNN layer, which is like a physics-based recurrent neural network, where they basically incorporate a state space representation of ordinary differential equations. And then there's the output of that is fed through some neural network layer together with the inputs directly. But let's forget about the right part of the figure for now. So that's the basic system. And then you're training both the parameters of the like the weights and biases of the neural network layer, but also the physically based or physically meaningful parameters in this state space model. Yeah, you could call it like a gray box model. I think in MATLAB you can do similar kind of things with using state space representations, but then learning the parameters or some of the parameters. And then, so that's the main pipeline. And then later in the paper, they also look at regionalization, so prediction in ungauged basins based on what they learned from gauged basins, where they basically train some network layers to map a big vector of catchment characteristics and map it to the parameters of both the physically based model and the weights for the neural network layers. So for the physically based model, it's basically a two-bucket mass conservation model, where the inputs are, so they have two storages, the snowpack and soil water. The inputs are the snowfall, which depends on basically the inputs are precipitation temperature and day length. And then that's split in a certain way to govern these fluxes. So one thing to note is that there's no other way to for precipitation to leave the snowpack than through melt. So there's no sublimation modeled in this conceptual model. Then there's rainfall, which I guess is based on the temperature, whether it would go to snowfall or rainfall, and then there's evapotranspiration, and there's the soil water that controls the runoff. So there's also no explicit surface runoff here. So that's the physics-based part. Then for the specific implementation, they also have the shortwave radiation and the vapor pressure as extra inputs, but they are not used by the physics-based part, but are still going into the purely data-driven layer. Any questions so far? Yeah, there's this other layer. Let me look for my notes. Which basically maps these catchment attributes to the parameters of the model. So they use that in some of the experiments, but in other experiments, this parameterization pipeline is not used, and they just use the main pipeline and train on each catchment individually. Then as a test case, they use the famous CAMELS data set. And they use 569 basins that have data from 1980 to 2010. So those are all in the continental US. And aridity is plotted here as well, because later it turns out that high aridity is tricky for models in general. So in the first experiment, they have 4 different models they compare. So this new hybrid DL model, deep learning model that they propose, and just the main pipeline of it. But then they have just the physical part, which is this green part, and just the common neural network model. So basically the 2 parts of the hybrid approach individually. And then for reference, they also have the long short-term memory neural network that Kretzert published about and built. And this is all trained on each individual basin, so that they fit the physics-based parameters and the neural network weights based on input and output time series, training on the 1980 to 2000 period, and then testing on the 2000 to 2010 period. So spatially, they all have most problems in the drier areas. So more in the central part of the US. They do have similar kind of performances, but the hybrid DL model actually performs best, or in some aspects. That can also be seen in the top figure here, which is plotting the 4 different models and the histogram of Nash-Sutcliffe efficiency values. It's clipped at the 0 here, so there's actually a few basins that perform worse. But you can see that in terms of the median, the hybrid DL model performs best, even outperforming the LSTM model here. Then this was I forgot for now, I think it's some kind of bias in volume. I don't have it handy here. So please step in if you remember what that was. And then the MNSE is a version of the NSE that's more sensitive to base flow.
Peak flow bias.
Peak flow bias. Oh yeah, that's the PFAB.
So it's absolute value of peak flow bias. That's where the A
Yeah.
comes from, I guess.
Yeah, and lower is better in that case, right? So then basically on all measures, the hybrid DL model performs best of the four that are evaluated. Yeah, let's forget about the bottom part for now. Then for the hydrographs, this is what they say a typical catchment. So you can see with some zoomed in details that the hybrid DL model outputs very natural hydrographs and is able to simulate the peaks well. The neural network part by itself doesn't do so well. And the physically based model also has problems in the peaks, but somehow together they can do very well. And the LSTM model is a bit less impressive in this example. Then in experiment 2, they basically try to model outside of the trained catchment. So they split it into 5 random sets. Let me say one important detail first, is that they throw away all the basins that perform badly first. So there's they retain 450 basins that are either having an aridity index of lower than 1.2 or have low precipitation days less than 280 per year. So basically they throw away the grayed out corner here in this plot. And that's because the models that are trained on the basins individually don't perform well there. So they want to basically see how well it regionalizes, but only for the cases where we can expect the model to do reasonably based on the individual catchment calibration. So the 450 basins still cover like a good part of the geographical scope, but generally the most arid regions are left out. And I think that has been observed in many studies, that whatever model you use, you tend to have more trouble in arid basins. Yeah, so they do 5-fold cross-validation each time, training on 80% of the basins and then testing on the remaining 5th that was not used in training. A note though is that they do use the full period for training and testing. So basically here they extrapolate in space to new catchments, but not in time. And while in the previous experiment they extrapolated in time, but not in space, but they don't do both at the same time. And then for this experiment, they compare 3 different models. The regional hybrid deep learning, which is the model including the parameterization pipeline. So basically the model they propose in this paper. Then they have the pseudo-regional hybrid deep learning model, where they do fit one model to all catchments at the same time, or at least the 80% that they use in training, but they don't allow the parameters to vary between basins. So they don't use this parameterization pipeline, but they do try to find a good set of parameters that works for all basins, which is of course not expected to do as well as the first approach because there's less flexibility. And then the last model they compare with is the regional LSTM of Kratzert, where basically they concatenate the vector of basin characteristics with the input data. So the model has the freedom to learn the behavior of individual catchments based on the characteristics. So the results for that are in the lower panel of this figure. So actually, indeed the regional hybrid model does better than the pseudo-regional because it has this increased flexibility of adapting the parameters to the specific catchment conditions. So that's a significant improvement. And then compared to this other regional model based on LSTMs, the median is a bit lower, but the mean is a bit higher. So basically they claim that it has less very bad catastrophic modeling outcomes. Yeah, so maybe the overall the performance is a bit worse, but it's a bit more stable at least, which may be attributed to the fact that there's more of these physics-based constraints to keep the model in check. Yeah, so the interpretation they make of these results is that indeed the hybrid DL model has a lower median but less very bad catchments, though it's important again to note that they first removed the bad performing or the worst performing catchments for this hybrid DL model specifically. We might argue that probably the LSTM would have trouble in those situations as well, but of course it might be considered a bit biased to first exclude those catchments. And then the counter to being slightly less performing in the median is that the hybrid model is better interpretable because we have this physics-based part that links the form and the function of the model and the actual catchment. So one way to view this approach is like as a streamlined parameterization model for that original conceptual model that they had. Then they asked the question, can the hybrid model reason? And classically, we've used the Turing test to see whether an AI can reason. But since ChatGPT passes that by just outputting a blurry, compressed version of the whole internet, we cannot really use that test anymore. So the authors propose that the new test for reasoning is whether you can simulate snowpack or not. And they tried that by looking basically at this snowpack bucket of their conceptual model. And then for all 450 catchments in this regional study, they calculated the average snowpack based on this S1 storage across 450 catchments. And they compared that to the average snowpack independently measured with remote sensing over those same 450 catchments. And the results are, well, I find astonishing. It's an extremely good fit. So that was impressive. Yeah, so the conclusions of the paper is that this symbiotic integration works quite well and is promising. The deep learning layers can kind of fill the gaps of the physically based models. They also note that the framework is very flexible, so you're not tied to using this specific physically based model or this specific neural network layers, but you can exchange it for better versions that take more processes into account, or the newest developments in deep learning for the deep learning part. Yeah, so that's basically the summary of the paper. So any remarks or caveats that anyone found when reading the paper?
Awesome, thanks, Steve. I'm gonna be sharing in the chat a file where we can collect the main ideas of the discussion. So feel free to include your contributions there, please.
Okay.
I'll just mention something that some of my students remarked when they read the paper, which is that snow image that you're talking about, that's the average over the entire set of basins. So in some sense, that's not highly remarkable. It's not clear that actually tells us very much, because you don't know how well it's performing at any individual basin. All you're just saying is on average, it's doing well.
Yeah, so I guess the question is,
you have to be a little bit cautious with some of these results that have been shown.
Yeah, I think one of the questions is what's the benchmark, right? Maybe for modeling the SWE over 450 catchments, a simple regression model with temperature and precipitation would do just as well. And in general, I think that's also with these NSEs, right? Like there was this paper by Bettina Schäfli a long time ago, like, do Nash values have value? Where basically it's a comparison with the average, right? That's the benchmark. But maybe if you have like a very simple basin with a big seasonal cycle, if you would just fit a sine wave to the seasonal cycle, you're already maybe at an NSE of 80%. And that's maybe one of the reasons why these arid basins are more tricky, because you actually have to get the dynamics right instead of just keeping the rough mass balance correct.
Certainly that's true, but there's also some compelling evidence from Luis's paper that a big reason is just that the data in arid regions is not sufficiently informative. So, Jonathan, have you had a chance to plot up your results yet with aridity? Marvin's plotted up his data. Luis plotted up his data, where we plot model performance regardless of the model type against aridity index, and the performance drops off dramatically in arid regions regardless of the model type you use, suggesting very strongly that the problem's actually in the data.
Okay, yeah.
I actually had forgotten to make those plots, but I can make those.
Okay, reminder.
Today.
Okay, cool.
Yeah.
So I've contacted 3 different groups independently to plot their results that way, and we're thinking of trying to do a small discussion based on that. Because what you see is in the humid catchments, regardless of the model type you use, you get fairly high performance, but in the arid catchments, you get a huge variety. In some cases, good performance, in many cases, really, really good performance. And it doesn't matter what modeling strategy you use.
Yeah, and I also wonder how much that is related to the stream flow measurements, because if you are in an arid
Generally,
place,
model
you
quality.
probably don't have the peaks in your rating curve.
Well, it's even worse in arid regions because you're not sure that you have accurate precipitation measurements.
Yeah, that's the other
It's
side
even
of it.
worse. But regardless, the question is, what's the state of the system that you have to track? And Luis has a paper he's working on right now, where he applied LSTMs to different catchments across the country. And he found that the amount of sequence length memory that you have to feed the catchments is directly proportional. The length you have to feed is directly proportional to how arid or wet. So to how arid it is. So wet catchments have very short memory, and arid catchments have, in principle, very long memory.
I think that this is like one of the things, like whenever I see these papers with the hybrid models, like in every step of the way, you kind of have to like think about how you're going to do the hybridization. Like if the sequence length changes with the aridity of the basin, you kind of have to think about how that hybridization works. But with like a pure deep learning model, you kind of don't have to really think about it. You can just change it. And same with like if there's a new parameter that will inform the response at one basin than another. Like I just saw some results like adding, some physiographic parameters like drainage density improves performance under some conditions, and you can just add them. And like the baby can learn like all of this stuff instantaneously, but the professor takes a while to figure out how to make use of it.
But yes and no, because he fed in the same very long sequence length to the LSTM, trained to all the basins, and then he trained individually different sequence lengths on each basin, and you get much better performance if you allow the sequence length to be basin dependent rather than some generic parameter. Because the problem is then it tries to use the same sequence length for every basin. And now you're having to train a system where some of the things that just not informative. Whatever.
So with sequence length, you find that if you make it too long, it deteriorates again. It's not able to just figure out what to forget by itself.
That's correct.
Okay.
That's not to say that one couldn't build in, but you would have to build in an additional network which learns the sequence length for each catchment, which is not there in the current LSTM formulation. It's not saying you couldn't put it in.
Yeah.
But it's part of the hybrid between the professor and the baby idea, is you have to know what you need in your network, and or something which we don't quite understand. If you're saying the generic network can learn all of this, the question is, does it have the architecture and the training mechanism for actually learning all that?
Yeah. Yeah, can we actually, why can't we expect the network weights itself to take care of forgetting the irrelevant information? Isn't that kind of the promise we have with AI, that it will learn which inputs are relevant without an extra external loop?
Don't forget that it's using the same network weights for every catchment. And the only way that it would use different networks weights for different catchments is if it allocates different parts of the network for each catchment.
Okay.
And
So,
so
so
that
the,
you'd have to add more layers.
Yeah.
To capture that.
so the mapping of catchment attributes to the parameters don't influence the weights individually for each catchment?
Not in a. Go ahead, Jonathan. You know better than me.
Yeah, they won't influence the weights that have been trained, but they will influence the nodes in the network which are used to make the prediction.
Yeah, so the loading of the, yeah.
So this sort of relates to the lottery ticket hypothesis, which basically says that if you train a very large network, only a very small part of the network will actually end up being active in any given situation.
Yeah, I
Stephen?
Yes.
Go ahead, Jonathan.
No, it was on the same topic, but we can move on.
Okay, but I had a different question, so you may want to complete this topic first.
I was just going to give an example of that. I train a neural network to predict the flooding extent in a bunch of different administrative units in South Sudan individually. And then I try to train a network to predict them all based on their attributes. And it wasn't having any luck with that until I extended the complexity of the model enough that it basically, there were 60 admin units in South Sudan that I was trying this on. I basically had to have a network that was 60 times as big as each the individual ones. And so then it kind of hit me like, oh, it's learning all of them at the same time. It's not as much cross information between like the admin units or the catchments or whatever.
And did you still find an improvement with that more complex network, or?
There was not an improvement, but the result, it was the same, basically the same results.
Okay, yeah.
But if you have crosstalk, if there's common information, then presumably you would get some benefit.
Yeah.
So Stephen, I do have a specific question about the paper. In the last comparison with the regional models, the LSTM they used from Freddy, was that also trained on this, weeded out subset of well-behaving catchments, or was that the original that was trained on all, and they trained their hybrid models only on the well-performing, well-behaving catchments, which would then be a little bit an unfair comparison?
Yeah, that's a good question. I didn't get that from the paper, actually. Yeah, so I'm not completely sure about that.
Me neither.
That's quite relevant indeed.
So it seems I'll just have to revisit the paper.
Yeah, well, for sure, it was not mentioned in the main paper. It could be that it was somewhere in the supplementary material. And actually, they do provide a code, which I didn't have time to dig into, but I'm not sure if they trained their own LSTM from Freddy's code, or whether they just used the results from his paper directly. Yeah, so what do we think? Is this the way forward? I was thinking, like, would it be beneficial to have more inputs of the neural network layer coming from all the states in the physically based model as well?
I think these are open questions.
But aren't you working on solving them?
Yeah.
But you're not done yet.
Yeah. I think considering this field really blew up in like 2017, 2018. We're like 5 years in, which
Yeah.
in the grand scheme of things is pretty short time period. Considering probably a lot of rainfall runoff theory was developed over hundreds of years, if not thousands. And yeah,
I think one of the key
I don't
things
think there's a clear answer on what's going to end up being best, but most situations where I've seen that they've tried to take like states of a physical model, there's no clear benefit of that. There might be like comparable to a pure neural network, but I haven't seen hardly any papers that say that there is a clear benefit, and when you do see those papers, they're like a very specific scenario.
Okay. Yeah, and then I think Gray did some experiment with a mass conserving LSTM, right? But that didn't work very well.
Right.
And that's also one of the issues I have here, is that for the physically based model, they enforce mass balance, but they don't model any like interception flux or sublimation from the snowpack. As just one example of like something that would break that mass balance for that model. So I can imagine that just using the conceptual model won't work, and you need the other layers to kind of compensate for that then.
Well, the main contribution of this strategy is to give you a basis for embedding hypotheses into a machine learning framework. So your model becomes a hypothesis, and you still have to, in a classic machine learning approach, the hypothesis is hard to interpret because you don't know, what the structure of the hypothesis is. So the difference here is that you can embed your hypothesis into the network, and you can test whether it has value.
Yes, but wouldn't the black box part of your model, couldn't it secretly learn to compensate for your hypothesis without you knowing?
Well, that's where you're testing. That's where you're testing it with and without the hypothesis.
Okay, yeah.
Because be aware that if you don't put a hypothesis in, you're still plagued by the training problem. You still have to know how many nodes, you have to train the parameters, you have to have enough data. You have all of that. One of the regularizing effects of hypotheses is to essentially reduce the degrees of freedom of the problem. That's essentially what you do when you put in a hypothesis. And so you're asking the question, if I reduce the degrees of freedom with this particular hypothesis, does it help reduce the training problem? That's part of it. And then does it actually add value by constraining the model space, the model representation to a particular part of the space, so that partly you don't have to search the rest of the space, and partly does that part of the space actually add value, just restricting yourself to that part of the space. And then you should test it for extrapolation, of course, which is another conversation. What's really extrapolation?
Yeah, because that's something that struck me, that they didn't attempt to extrapolate both in time and in space at the same time, which is maybe one level too tricky for the model. But I think still, yeah, with both these experiments, you couldn't get away with a fully overfitted model, right? Because it still wouldn't wouldn't extrapolate well in time or in space.
Part of the problem is we have to define extrapolation. What's his name? Uwe's colleague. Manuel, what's his name? The other guy across the hall from Uwe.
Ralph Lauritz.
Ralph, yeah. Ralph Lauritz and I had a nice conversation about this. In fact, he's going to present an abstract at EGU. And so the question is, what is really extrapolation? If I give you some data points, right, in XY, okay, and I fit a line through it, okay, and now I test it against some new data points generated using the same process. That's extrapolating beyond the range of the data, but it's not extrapolation in the sense of testing it under new conditions. Right? Because the generating process is exactly the same. All that happened was that my smaller subset of data actually did contain enough information about the nature of the process, and I was able to learn it, which allows me to extrapolate beyond the range of the data. But it's not extrapolation in the sense that we're extrapolating into a new regime. Okay. So the paper that, was it Marvin Gouch? No. What was the paper, Jonathan, that Freddie and...
The proper care and feeding of camels, that one?
No. The other one where they actually did test for extrapolation, so to speak. Where they withheld some of the data.
The extreme events paper?
Right. Was that yours?
Yeah, that was mine.
Yeah.
So there, that one we held out extreme events based off of the return period of the peak flows. And so whatever the peak annual flow was for any particular year, if it was above 5-year return period, we left it out of the training data.
And it did well, right?
It does well, but the thing is, since it was trained on every single basin, an event that's a 5-year return period on one basin could be a 25-year return period on another basin. So it's seen that event just in a different basin. And so in that whole set, throughout all of over 10 years, throughout all of the United States, there was only 3 events that were not in the training set.
Right.
But still the model performed reasonably well on those. And so there's only 3 true extrapolations. If you take all of the runoff events throughout all of the country over a 10-year period,
right,
there's only 3 events that haven't been seen anywhere.
Yeah, so in that sense, it's not extrapolation because you're saying in the sense that I'm talking about, whereas if you now, find that the model just absolutely falls apart, now you've got new information to learn something about the process there, which wasn't in the original data set. So this whole conversation about extrapolation, that's why I found that paper interesting, Jonathan, because you were basically pointing out that it wasn't really extrapolation because the information required to learn the physics was actually there in the data set.
Right. So if you, in that graph that you're showing, if you have, a set of intercepts and slopes, and you can choose the one that fits the scenario that you're looking for,
right?
You can train to, I'm going to use this slope and this intercept over all these conditions, and then there might just be some subset of data that no trained slope or intercept has seen.
That's right. Yeah. And that's where we learn. I mean, that's where our real scientific learning occurs, right? When our hypothesis completely falls apart, but it's part of the reality. So we've got to go back to the drawing board. Yeah.
then if you use the whole internet as the training set, then maybe you don't need to extrapolate anymore.
Well, did you just read
The
that?
internet has all the information you want, but I don't think that is a reasonable assumption.
Did you read the paper that Dan sent out? I think you would.
Yeah. Yeah, and I was wondering, like, is the internet we have now like a pristine, pure form of human information that now will get polluted by the outputs of these generative AIs, and it will never be the same because now we're training on our own polluted data set, right? It's like, well,
we do that all the time when we let people influence us, right?
Yeah, like it's just regurgitated information multiple times, I guess.
People stop thinking for themselves, and then you go off on a tangent. Yeah.
But in a way, then we don't have that problem in physically based model or in the geosciences, right? We're not mixing up our model outputs and our raw data. So.
Well, we have a problem whenever we try to combine models.
Yes, yeah.
But I actually think we do, because a lot of the, I mean, maybe not in, yeah, even in streamflow, I mean, you measure a stream gauge, you have models that connect the sensor with the output, you know, the rating curve, but also if you have a optical stream gauge measurement, that also it has models embedded within it. So I think in some sense we are, especially a lot of the data, you know, the input data comes from atmospheric models that we take as the observation.
Yeah, that's very true. But at least it's not training a model on the outputs of the same model, but indeed it's a cascade of models. So maybe we should build a repository for only the raw unprocessed data of everything, and just feed that into a one big deep learning model and see what comes out.
So the discussion about compression and what he decides is lost, it should be thrown away, and what should be kept, right?
Yeah.
That sort of supports your argument there, because somebody else might go back to the raw data and decide to do a different kind of compression and learn something completely different. But anyway, what was your opinion of the paper, Stephen?
Yeah, it surprised me how well it worked. I'm also always a bit suspicious when I see very good results, so I didn't have time yet to dig deeper into the results, but yeah, we have played a bit with Freddy's models, and initially we did get these strange results that if you put in random catchment attributes, you also saw an improvement in performance. So that was, but it turned out that we did something wrong with the validation set. But yeah, those kind of things, I think there's so many steps where you can kind of miss a setting, and then you're overfitting without knowing, that you have to be very careful with interpretation of results. Still the snowpack results impress me. I see what you mean with the averaging, which maybe makes it a bit less impressive, but
that's another thing, Stephen. The other reason why I was thinking it would be good for us to follow up on those plots is because I'm sort of arguing for the fact that we need to identify the problem basins, right?
Yeah.
And then we need to resort, and within those problem basins, we need to identify where the problem is entirely due to data and where the problem might actually be that we just haven't learned the proper physics. Right? And that could help, because right now there's a tendency for people to just show their best results. And the question I always ask is, well, that's median performance, but that means 50% of the basins are worse than that. And you just want me to look at the 50% that are better, but we should be looking at the 50% that are below, right? Or the bottom quartile or whatever. And if you're going to advance the science, that's where we need to put our focus.
I think what Jonathan mentioned, like how far this field has come in the last 5 years, I think it's for a big part due to how much of the under the hood stuff is shared with papers now, which really makes a big difference in reproducibility. And so yeah, I'm quite hopeful actually that this will keep on accelerating. Yeah, so basically, even though the paper doesn't explicitly look at the worst cases, anyone actually can do that. So that's very good compared to the past, I think.
Yeah, I loved the paper when it came out. I mean, I still like it because it did something novel and new at the time. And we can criticize it in hindsight, but that wasn't the point. When it came out, it made us think things in a different way. So.
I also think that it emphasizes that there can be synergies between both approaches, like combining, like maybe that is the next step forward, combining the best parts of both approaches.
I think that's definitely going to be the case. And I think even when there's like a pure neural network model, it still combines a lot of the lessons that were learned from all the conceptual models over a long period of time, just in like I mean, one of the main reasons that field blew up is because of the CAMELS data set, which has all of these variables in it that were collected and put together, but they were only collected and put together because those were over some period of time, those were identified as these are the bits of the specific variables that we need to complete the data set. And it's not complete by any means, but it had all the information there that allowed people to start really digging into it.
Fair enough.
Any other thoughts about this paper?
I also was trying not to look at it through the lens of 2023, but trying to look at it more towards what it provided in 2020. So I think it's a nice capture of the momentum to do hybrid modeling in 2020.
And what would you say is the current state of the art in that, or do you still believe hybrid modeling is the way to go? And what's the current state of the art according to you?
I think that I still think hybrid modeling has a lot of promise. I think that Xiaopeng's differentiable models are, if not the state of the art, they're close to it. So in Xiaopeng's models, he's training a neural network in LSTM to predict the parameters of a conceptual model at every time step. So at time step 1, the parameters for that control infiltration are different from the parameters at time step 2, and these were all learned through an LSTM. I think that's that's a reasonable approach for hybrid modeling.
And that's done in a way that it still conserves mass, or by changing the parameters midway, you secretly lose some mass somewhere.
That's a good question. I don't believe that there's anything in the parameters of, he's using HBV. I don't think there's anything in the parameters that if you change them, that would lead to any loss of mass through the conceptualization. But again, like your point, the conservation of mass through the conceptualization of HBV doesn't include all of the fluxes that are in the natural system where the mass would change.
Yeah, and then also in the data, you're not having a complete coverage of, you're not checking the whole control volume, right? You're checking a few points and then interpolating a bit. Checking the whole control surface.
This whole thing that physical models conserve mass is a bit of a red herring, because they don't. They only conserve mass in an interpretable sense, not in a real sense. I also think that the terminology hybrid modeling is kind of misleading. We just have models which are regularized more or less. And it's the kind of regularization that we impose, right? We're using hybrid models because we want them to have properties that we predetermined they should have. Yeah, and they should be interpretable in a particular way. But that's just regularization, right? And the reality is we're never going to have all of the observations needed to completely conserve mass. It's just not going to happen. So all of our models are always hybrid in the sense that they use mass, energy, and information flows and figure out how to optimally extract information from them. The term hybrid just really refers to us saying, I can interpret in a particular way.
Do you think at some point there will be like a very common language for, be data-driven models, physics-informed models, theory-informed models, all this stuff? At some point, it'd be nice to land on a common lexicon for them.
Well, we love to classify, don't we? So things are either more or one, and they're all, you define a set, but anything is really fuzzy in its membership. The only models that fit precisely into a set of the artificial ones we create. Like geometric models they don't exist in the real world. They just exist within the confines of the abstract limits of geometry. The real world is always fuzzy. But I do think that since we have developed a fairly strong scientific base on conservation principles, that we can think in terms of those as being strong regularizing constraints. We just need for our models, even if they are regularized by conservation principles, to be able to violate them because the data won't. We can't hold the data to adhere to them strictly. For example, GR4J, the model which comes out of CNRS, allows you to learn unobserved mass exchanges with the environment.
I don't have much more thoughts about it. Does anyone have anything important about this paper still?
Well, the question would be, if we were to do this again today, what might we do different? If somebody were to repeat this study again, knowing everything that we know now, what would we like to see happen? I'd like to see multiple architectures in there, for example.
For the physically based part, or in general?
Yeah.
Like,
Yeah, for different parts of the world. I'd like to see different, I'd like to see different baselines that you mentioned up front,
Yeah.
saying, what's our target that we're trying to improve over? What does it mean to have learned a good model, rather than comparing to the long-term mean? And I'd like to see something which recognizes that humid catchments are different from dry catchments. Something.
and I want to see the performance outside of those 450 basins.
Okay.
That would be nice.
Yeah, actually, I think the idea of like cutting out some of those poorer performing basins is a little wonky. And I think with the amount of data we have now with the caravan data set, that's, global, but we have like all of the, camels, Brazil, and some of the European data sets. We have a lot more opportunity now to do more robust out of sample studies. There have been several studies that have been doing prediction in ungauged regions more systematically, either training on one continent and trying to predict on another continent. So I think that's something that's important to really consider.
That's Go ahead,
Sorry.
John. Yeah.
If the goal is to create a general, rainfall runoff model that can be used, that has the correct information to be used anywhere, then testing it everywhere is important. And in those true out of sample conditions, out of sample in time and space, if you have a basin in space that's out of sample, but then it's adjacent to another basin that's very similar, that had a similar event because it was also in like a flood year, and that's not really that far out of sample. So there have been out of sample regionally studies have come out recently, and Xiaoping's differentiable model is one of them. They submitted a prediction ungauged regions paper with that model being used.
Okay. Yep.
The other thing that strikes me, Jonathan, is that prior to putting together things like the Camels data set and others, the whole discussion about large sample hydrology, prior to that, there was the tendency was to try to look for a set of characteristic or typical basins, right? And this almost really suggests that that doesn't really exist, but that you have sets of more similar and more different basins, but that you can't just pick a single basin and expect to learn everything you need to learn about hydrology by just studying only that single basin forever and ever, which is kind of what we were constrained to do before these large sample data sets started to get put together.
Yeah, totally. Another thing that has come out after 2020 is there's been some papers like clustering basins within camels, and it really shows that you could have a basin in Florida and a basin in Washington, and they're more similar than their adjacent basins. And so like the reference basin idea isn't as easy as maybe we thought it was at one point.
At least space is not the defining characteristic, it's something else, right? Yeah. Functionally.
However, I think also I do think that like one thing is a local expert, if you're some sort of water manager in the Central Valley of California, and you intimately know the hydrologic responses and all the different watersheds in your region, I think having that experience and that like local expertise allows you to do that. But just looking at large data sets might not allow you to capture that.
Well, one of the interesting things was that prior to all this work was when they tried to do clustering, the classification of basins, almost the first 2 or 3 characters that came out were all hydrometeorological. They had nothing to do with the land surface. And that's kind of a cop-out, because what you're trying to learn is the transition function between the input and the output, which is a secondary response. But if your catchments all have the same inputs and outputs, that you're not learning that. You're just learning that these have similar hydrometeorology, not that they're actually similar transition functions.
This is something I'm struggling with right now, trying to look at that space of, or looking outside of the space of just like 2D space for what's similar, right? How are 2 basins similar, and looking at all the attributes. For a few reasons I'm struggling with it, but maybe I'll just ask the audience. I've been trying to do some like feature importance analysis, and that I'm not really getting any kind of results that demonstrate much of anything to me. But there's clearly differences in importance of attributes, and I'm wondering if anyone can recommend some other work that has been done on feature importance.
By features, what do you mean?
Attributes.
Sorry, you're just using another word. Need to
yeah, physiographic, land use, land cover,
okay,
soil.
So the first thing I would want to do, but I haven't figured out how you would do it, is I would want to somehow normalize or control for hydrometeorology, right? In classical statistics, that's what you do. You run the control experiment. So you somehow have to normalize out the influence of more rainfall, less rainfall, temperature, all of that kind of stuff. The interesting thing in Yuan's paper on snow was that when you ran the LSTM to do snowpack dynamics, we found that to first order, the local land characteristics didn't matter, which actually makes sense, right? In other words, hydrometeorology governs 90% of the performance of the prediction of snowpack from hydrometeorological variables. And when we added in local characteristics, or when we went to a regional model, or we tried to go to a pixel by pixel model, there was not a dramatic or significant improvement. So that was an example of a situation where local characteristics maybe were not that important, right? And even information about elevation is sort of encoded into hydrometeorological variables indirectly through pressure and temperature and all this other kind of stuff. So if you guys can figure out how you control for the hydrometeorology part of it, then maybe we have a possibility of being able to parse out which parts are similar and which parts are different, because there's so much noise which is just there in the input, and all we end up doing is just classifying things based on the inputs or the hydrometeorology.
I guess the closest thing I've come to approaching that is to sort of stratify distances. So if I just take all of the pairs, and that are pairs of basin centroids that are within, say, 100 kilometers, and then say look at those compared to 100 to 200, and then increments of 100 kilometers. That's the closest thing I've thought of to try that, just assuming that the inputs, the hydrometeorological inputs, will have a better chance of being more different as you go further in space. But
what if you could normalize on the hydrometeorological inputs and then somehow store something about that normalization. Like, so in rainfall runoff modeling, the runoff ratio would store information about the relative normalization, right? So you put your rainfall between 0 and 1, you put your runoff between 0 and 1, and then you store the runoff ratio as a characteristic property. Now all of a sudden, basins, it would have to be something different than the magnitudes that would be the defining characteristic. Right? And that runoff ratio is a property of the transition function. It's not a property of the original range of the data. I just don't know how you pursue that further, but that was sort of the thing that was, I'm thinking of like in classical modeling, you have the impulse response function, right? It's the impulse response function that's a defining characteristic of the transition between input and output. And it doesn't matter what the magnitude of the input or the output was. It's like, how do we use the data that we want to pin down on not the data itself, but the transitions between the data sources, which are really what our model is. Presumably soil moisture holding capacity, whatever that means, would be part of that because you've got less soil or more soil. The complication there is that only the top meter might be active in some places.
And it's so different across the basin.
Yeah.
Those kind of physical variables are just so heterogeneous. It's tough for me to imagine that an average across a basin is going to tell you as much.
Probably not, but maybe some distributional property might work because it's a low pass filter, right? Basin. If you're just talking about stream flow at the output, you really probably can get away with just looking at the distributional properties rather than it's not the average and it's not every single value. It's something in the middle.
I have to get going. Hoshin, I'll make those plots today. Sorry, I forgot about that.
Sure, that'd be great. Thanks.
And Leila, I think I volunteered to go next time. So should I just if I'm still on the agenda for next time, I just pick paper?
Okay.
Which
Yeah,
paper is it, Jonathan?
I haven't picked one yet, but I'll pick one and send it to Leila soon.
All right.
Awesome. Yeah, thank you, Jonathan. Yeah, and I left a couple of notes in the chat, in the file that I shared. So yeah, if you find something that I should be replacing there to be more concise, please do. And yeah, it's awesome to see you, everyone, and we'll see you in 2 weeks.
All right, thanks.
All right.
Okay. Bye.
Thanks again, Leila. Bye.
Thanks, Steven. Bye-bye.
Yeah, my pleasure.